wearable device is especially built for sports personnel who loving running, cycling, swimming, etc. These devices come with a GPS tracker and records information on the user's pace, heart rate, etc. So for the sports personals, this device is very useful. So the name is sports watches. Then smart jewelry. Smart watches are designed as jewelries, especially targeting women. These jewelries notify the users of their text messages, calls, or emails when their phone is out of reach. So it is like smart watches, but the design is somewhat like jewelry. So it is meant for women. The next is smart clothing. Smart electronic devices are incorporated into the wearable clothing. Is called smart clothing. So it is used to give an interesting and fashionable look. Uh, smart clothing is another kind of wearable device. So whatever the application we are finding in the previous devices, we can incorporate here also. Then implantable, these wearable devices are surgically implanted under the skin. So these are usually used for medical reasons like tracking, contraceptions, or insulin levels, and etc. So like we can have implantable type of uh, wearable devices. So these are the 7 types of wearable devices for different applications, different tasks uh, uh, for different areas. Next, examples of wearable devices. So under head-mounted wearables, you see these are the examples. With the different companies manufacturing these head-mounted wearables. For example, Sony HMZ-T1 is the head-mounted wearable device for virtual reality, like Google Cardboard or Google Glass from Google company. Then Microsoft HoloLens. So this lens, HoloLens from Microsoft company and the Jawbone company. So this is also a kind of head mount. Then Emotive company is uh, manufacturing this kind of head mount. So this head mount is especially for will act as electroencephalography. So EEG. So generally, we will take EEG using a big machine. But you see, this head mounting device can easily give the report of EEG. So this emotive company and like Sony Marcus. So this is for virtual reality, head mounting device for virtual reality. So these are Google Glass by Google company, contact lenses also. HTC by company. So these are the different companies manufacturing this head-mounted wearables for various applications. So similarly, wrist-worn wearables. When we talk about wrist-worn wearables, like the companies like Garmin, Fit, Jawbone app, then Apple, Garmin, Fitbit Charge. These are the companies manufacturing wrist-worn wearables, like smartwatches and fitness trackers. Uh, all these include. So these are the examples of wearable devices uh, manufactured by different companies. So nowadays, because of the technology development, the percentage of users also increasing. So that we will see this later. So next topic is considerations of wearable devices. What are the design considerations of these wearable devices? So if anyone want to design this wearable device, What are the design considerations? So first, we need to consider form factors. What is meant by form factor? Wearable device usefulness is determined by form factor, which is usability and applications. A device form factor defines its size, its shape, and how users wear or carry it. So, according to the place where we are going to fit this wearable device, we have to design the size and the shape of the wearable device. So, for example, the identified form factors are anklet, armband, backband, belt, bra, bracelet, contact lenses, chest mounted, earring, earpiece, glasses, glove, headphones, head mounted, helmet. It can be in the form of jacket or necklace, pajamas, pendant, ring, shirt, shoes, watch, wrist mount. So, so these are the form factors. So we need to identify the place where we are going to fit this wearable device, or or the size and shape of the wearable device, or the size and shape of the wearable device is determined according to the form factor. So suppose, for example, if you are choosing the form factor uh, uh, like a ring, we cannot have the big size. If we choose the form factor like shirt, the size may be some big size. So like that, if it is shoes now, the size will be different, shape will be different. So like that, we have to choose the form factor for design consideration. And then types of wearable. When we talk about types of wearable, we can categorize under three types. One is in the body, then on the body, and close to the body. In the body, like bionic eye, smart pills, smart implants, dental hearing, artificial limbs. So these are the wearable devices inside the body. Um, yes, and then we can categorize the wearable devices like EEG, EMG devices. EEG means electroencephalography. It is, so now I showed no. So this one, emotive. So emotive is the head-mounted device. It is used to measure EEG of the person. So EEG device, it is on the body. It is on the body. EEG device, hearing aids, 3D motion sensors, electronic glasses, sensor patches, electronic tattoos, insulin pump patches. So these devices will come under on the body. And close to the body, so like brain control headsets, wearable alarm system, GPS tracker, headset displays, sleep monitor, smartphone accessories, and emotion monitor, clothes and shoes, wearable cameras, activity trackers, smart watches, wearable controllers. So these will come under close to the body. So these are the three different categories of wearable devices. Then when we talk about uh, the cumulative wearable devices shipments by device category, from this graph it is very clear uh, the maximum shipments takes place for the wearable cameras, then next to body sensors, then next to fitness trackers. So the maximum used devices wearable cameras. So from this shipment graph, and also user preferences. When we talk about user preferences, 29% is clipped onto the clothing. See, 25% of the 29% of the users, they want devices which is clipped onto the clothing. So 28% of the users, they are liking devices in the form of wrist. If it is the form factor is having wrist, so it is very comfortable. It's user preference. 18% they are preferring clipped on shoes. 15% they are preferring embedded into clothing. So embedded into clothing is 15%. Clipped on the onto clothing is 29%. Then mm, like tattooed into the skin is only 3%. Very very less percentage. Then like contact lenses also only 4%. Then around chest is 6%. So like these are the user preferences. So from this we can understand user preferences is more percentage clipped onto clothing or a wrist or clipped on shoes. Then next only embedded into clothing. So these are user preferences. Then next, so when we are designing electronic devices, we have to consider all these uh, parameters into the mind, so that uh, the market will be we can make better market. Then implementation of the wearable devices. So where we are using these wearable devices, in which are the areas it meant for, where we can implement this wearable devices. Uh, Five areas are identified. One is medicine, then risky professions, then education, then office environment and industry, then sports and recreation. So in medicine, patient health monitoring and early detection of disorders allowing timely medical interventions. See, once the disorder happen, it is very difficult to treat in medical industry. So early detection of disorders is very crucial for medical environment. So in medical environment, these wearable devices can give early detection of disorders. It is very useful for the patient. Then next one is risky professions. Risky professions is nothing but when we are monitoring of the workers, like when we are doing construction, mining, shipbuilding. So monitoring of the workers is very important, a risky profession. Stay to prevent dangerous situations or potential injuries, particularly common in construction, mining, and shipbuilding. So using this wearable devices, we can easily monitor the workers, and also we can avoid many uh, major injuries, or immediately we can do the prevention. Uh,
லாஸ்ட் டைம் கொடுத்தேன்ல கீழே
Risky professions.
அது நான்கிட்ட கொடுத்துருக்கீங்களா?
And next, education. So in education, it is used to monitor the condition of stress level and the health condition of um, students. So stress level and health condition monitoring can provide a suitable foundation for the development of personalized learning plans, time management recommendations for scheduling of the classroom activities. So, uh, so, so using this wearable devices, we can easily identify the stress level and the health condition monitoring of the students and whoever we want. Then office environment and industry. So in the office environment, there is a chance of monitoring occupational stress. So occupational stress can cause the deterioration of health conditions, uh, implying that the monitoring of the health parameters of the employee can be beneficial in preventing such occurrences. So mostly we will concentrate on physical health. We will not concentrate on mental health. So, but in even in office environment and industry also, uh, there is a chance of getting occupational stress. So that can be identified by using this wearable devices. Like early detection will not, mm, if it is early detected, this occupational stress is detected earlier. So we can avoid this deterioration of health condition. So it will indirectly affect the health of the human. So that can be avoided by using these wearable devices. Sports and recreation. Monitoring of parameters related to training activities for a sports person, because a sports person needs a continuous training. So monitoring of the parameters related to training activities and also health conditions allows the prevention of injuries, achieving optimal fitness levels, or accessing sleep quality. Because when they are doing continuous training, a sports person, sometimes there is a chance of getting injuries. And also the fitness level is not too much, so it will affect the health also. So the fitness level also monitored, and assessing sleep quality, that is also important for a sports person. So everything is monitored by using this wearable device. So there is a possibility of so these are the main areas we can implement these wearable devices. So next, to the need for wearable devices. The wearable technology aims to influence the fields of health and medicine, fitness, aging, uh, disability, education, transportation, enterprise, finance, gaming, music, etc. As already discussed. The goal is to smoothly enter the daily lives of individuals and become a functional part of them. So, so again, these devices we cannot consider it is extra care, but it is not extra care. The goal is to smoothly enter the daily lives of individuals. Um, and then the hands-free nature of the wearables computing devices makes it very useful for the business. So because when we are doing business, some of the devices we are using hands. We are, we are using or this application using hands. We need hands to access the device like that. But these devices are or a head mountable, or it is wearable, right? So wearable. So no need to take it separately using our hand. We have to our daily wear. We can wear the device so that so automatically it will take care of it. So that is what hand-free nature. So wearable computing devices makes it very useful for business. Then tracking the emergency and rescue team becomes easy, thus making the workplace more efficient and safe. See, all these devices can be used for tracking and emergency rescue. So we can make it efficient workplace. Hand-free access. Again, this hands-free access to important data and information through smart glasses and smart watches helps researchers, engineers, and technicians to be more efficient at their work. Because of this hand-free nature, it helps researchers, engineers, and technicians for the efficient work. So these are the need for the wearable devices. So next, the key challenges of wearable devices. So when we talk about key challenges, uh, so wider use of wearable technology, enterprises see wearable computing as one of the biggest opportunity to drive efficiency and improve communication and workflow. So like mobile technology, wearable technology is looked upon as a disruption in the world of business. However, the growth and popularity of the technology always comes with concerns on power. See, mobile technology, we can expect in future wearable technology. Yes, wearable technology is also in future it may be the important one. So without this wearable technology, we cannot live. The time may come. So, so in this case, wearable computing is one of the biggest opportunity. Wearable computing is also one of the biggest opportunity. So whatever it may be, wearable technology or wearable computing or wearable technology. So in the smart world, the devices for wearable technology utilizes numerous autonomous sensors which requires. So finally, all these technologies devices consist of smart IoT devices, or in other words, we can say sensors. So these sensors needs or requires off-grid power source that lasts the lifetime of the devices, miniaturized and cheap. So we can say the power. So the design in this key design challenge of wearable device, we can include the power source for the devices is an important design challenge, and also the size and the cost cheap. Off-grid power, okay, maybe off-grid power or a power source that lasts the lifetime of the device. So for this, energy harvesters satisfy these needs with the effective and efficient power management solutions through scaling and material development towards nanotechnology. So how can we solve these requirements using which technology, using which device? How can we achieve these key challenges? So they are saying these energy harvesters. So if we design energy harvesters, it satisfy these needs with effective and efficient power management solutions. How this effective and efficient power management solutions we will get? It is through scaling and material development towards nanotechnology. See, nowadays, scaling means it denotes the how we are going to design the size of the devices. The size, if it is in a ring form, we need a small size. If it is placed in head, it may be in big size. So, like size. So, scaling is very important, and material development towards nanotechnology. So, which kind of material we are using for manufacturing that device? So, development towards nanotechnology. So, we need to use nanotechnology also, so that so material development towards nanotechnology and the scaling. So, it will give the efficient power management when we are designing energy harvesters. So, energy harvester plays an important role in the design of uh, wearable devices, and also we can say this is a key challenge. So next we are going to see energy harvesting solutions for wearable technology. When we talk about energy harvesting solutions, first we can differentiate two modes. See, if we talk about any wearable device, it can be battery operated or it can be operated with energy harvesting sensor nodes. If it is battery operated, uh, the device can directly take power from battery. So battery, then low power sensor, microcontroller, wireless transceiver, like that. So if it is using energy harvesting sensor nodes, so that time uh, ambient energy like solar, thermal, vibrational, wind, RF. So any kind of RF ambient energy is taken by energy harvesting device that is given to the energy storage device, then it is given to the wearable device. So like so here compared to battery operated wearable device, if we come to energy harvesting type, we need to design energy harvesting device, energy storage device. So extra design challenges coming here. So why we go for this energy harvesting sensor nodes? So because you see this graph, so this graph is in between stored energy and time. See, when we talk about battery operated, initially the stored energy is very high, but when time increases, it goes down, and after some time it is zero. So after some time we need to change the battery, so otherwise it will not work. But when we talk about this energy harvesting, you see the graph, there is a uh, there is a peak in uh, in the initial stage. There is a peak in initial stage, but after that it is going down. But at one point it is the energy is low, but immediately when it picks up the signal, immediately it is rising. So uh, it is like a continuous process, continuous signal. It means the energy for some time it is maximum, For at one point it is minimum, but again it is maximum. At one point it is minimum. So like it is continuous. See, anyway, we are getting energy continuously, and this when this continuous energy stored in a storage device, so definitely we can operate the sensors continuously. So that is the case. So from this we can compared to this battery operated kind of because we are going to some of the uh, in medical application for continuous monitoring, we are going to operate these devices continuously 24 hours. So for that, if we use battery, we need to suppose at the night time, manually we have to change the battery. It is very difficult. So if it is devices operating with energy harvesting sensor nodes, so we will get a continuous energy. So when it is stored in the storage device, continuously we can get the data. So that's the concept of going into energy harvesting sensor nodes. And another point, when we are using more number of devices, if we use only battery, so that time also it is very difficult to operating all the devices with battery, providing battery for all the devices. Cost wise also it is very high. And next, okay, if we go for energy harvesting, how much energy harvesting power can be tapped? How much energy tapped from various sources? So how much power is available for that? How much energy harvesting power can be tapped? How much power is available? So for example, if you talk about photovoltaic, if it is outdoor, 10 milliwatt power can be tapped. If it is indoor, 10 microwatt can be tapped. So if you use photovoltaic cell, if you use the vibration kind of
இங்க அத்தனை வேணும்
harvesting, yes,
நீங்க செய்ய
energy. If you use energy, there is vibration kind of sources like piezoelectric transducer. Piezoelectric transducer. So man means it is 4 microwatt power can be tapped. Machine means 100 microwatt power can be tapped. If it is thermal, if you use a thermoelectric generator, for example, thermoelectric generator, man means 20 microwatt, machine means 1 to 10 milliwatt power can be tapped. If you come to RF energy kind of harvesting, from GSM, we can tap a zero point 0.1 microwatt. Using Wi-Fi, it is 0.01 microwatt power can be tapped by using receiving antenna. Uh, Receiving antenna. So GSM Wi-Fi they have mentioned it is a microwatt power and 1 microwatt power. So in RF energy harvesting is less, but if we use array of antennas, it can be increased. So these are the just idea. So idea about how much energy harvesting power can be tapped from various sources. The possibility. See, next slide discusses about energy sources. See, when we talk about energy sources, again, it may be a light or vibrational or thermal or RF inductive. So each sources are having different challenges, typical impedance, typical voltage, typical output power, cost. So when we talk about challenge, conform to small surface area, wide input voltage range. So vibrational means it is a variability of vibrational frequency. So in thermal, the challenge is small thermal gradients, efficient heat sinking. In RF means it is the problem is coupling and rectification, design and rectification and coupling. So these are the challenges we are facing when we are when we are getting energy from various sources. Then when we talk about typical impedance, it is low kilo ohm, constant impedance. Here it is 10 of kilo ohm to 100 kilo ohm. Constant impedance 1 ohm to hundreds of ohm. Here it is constant impedance, low kilo ohms. So when we talk about typical voltage, using light 0.5 volt to 5 volt DC volt we can get. Then vibrational AC voltage tens of volts we can get. Thermal DC voltage tens of millivolt to 10 volt. In RF varies with the distance and the power. So 0.5 to 5 volt. So using RF we can achieve 0.5 to 5 volt. So this voltage is very much enough for powering sensor nodes. So typical power output, the same after discussing about voltage in terms of power, it is 10 microwatt to 50 microwatt. So for vibration, from vibration 1 microwatt to 20 milliwatt, from thermal 0.5 milliwatt to 10 milliwatt. So in RF is wide range. So from this, the cost is also like 50, $10 in terms of dollars. They are saying 2.5, 50, 1, 30, 0, 25. So these are the idea. When you use different energy sources, what about the challenges? What about the typical impedance, typical voltage, typical output power? See here, they are saying this is the report of January 2014. So they are saying energy harvesting types. We used January 2014. Vibration is 24% and vibration induction is 20%. Solar 10% used. Thermal 46% used. But after 2014, nowadays, many researchers, many applications, they are concentrating RF energy harvesting. So we have to make a note of this. Then various energies uh, surrounding human live environment and the generators that gather these energies. See, this inner circle denotes energies surrounding human live environment. This inner circle. In inner circle environment, um, in inner circle, one, two, three, four types. So energy types are solar. One is solar, two is thermal, and three is other energy. Fourth one is mechanical energy. Generator type denotes outer circle. If we talk about outer circle, it is solar, battery. See, solar energy is from generator type is solar battery, and the thermal energy from thermoelectric, pyroelectric generator, and the other energy is from hybrid generator, and mechanical energy from piezoelectric, electromagnetic, triboelectric. These three, four, five, six. These are the generators for mechanical energy. So these are the energy types. These are the generator types uh, available, or uh, we can we can categorize these one, two, three, four types energy, four energy types. These are the generator types under these four energy types. Energy sources. So here RF is not included. RF is not included because these are the data before RF energy harvesting started. So next, analysis of the possibility of energy harvested to power wearable electronics and clothing. So energy harvesters in wireless sensor networks. See, the kinetic and thermal energy originating from the user and the radiation energy from the environment is used as the main energy sources in the miniaturized energy harvesters within wearable wireless sensor networks. So in starting, most of the energy sources are kinetic and thermal. So the design starts with kinetic and thermal. So energy processing stages, which include energy, EH transformer, energy harvesting transformer, an input system, energy accumulation, voltage regulator, power system. So topology of the exemplary power electronic solution. So generally they used like this. So the energy is what type of energy? The kinetic energy or thermal energy. So initial time we used this concept. After that, Uh, After that, is kinetic energy and thermal energy. Initially we used this concept. Then, according to this various energy types, according to these various energy types, we can say the solar light solutions to capture electricity from solar radiation. See, in solar light, photovoltaic cells convert light energy into electricity by means of the photoelectric effect. So the ability of the matter to emit electrons when a light is radiated on its surface. So this photovoltaic cell is nowadays we are using organic type of photovoltaic cells, perform the light energy transduction using organic material either entirely or as a part of the plant. This organic photovoltaic is a new interesting way for light energy harvesting. This is a new photovoltaic technology. It's a practical alternative compared to the inorganic silicon photovoltaic due to its low cost roll-to-roll print processing. See, compared to inorganic silicon for photovoltaic, this organic photovoltaic is low cost. So more versatile and flexible also. So while still having the lower efficiency and short lifetime capacity, the conventional solar cells, organic photovoltaic cells are being increasingly tested as energy harvesters to be embedded in wearable devices, since they can be swim with the textile electrodes. See, this organic photovoltaic cells, even though it is less cost, even though it is very conventional, versatile, and flexible, the efficiency is very low. Efficiency is very low, and also short lifetime capacity. So these are the two drawbacks of this organic photovoltaic cell. Uh, Even though it is having some of the advantages, because of this disadvantage, we can go for some other sources or technology. Here is the example of how they are using solutions to capture electricity from solar radiation. The method of integration of the photovoltaic cell. Here, in short, the photovoltaic cell is t-shirt. Photovoltaic cell is fabricated. And in example of jacket with removable solar panels. So if we the jacket with the solar panel, you can uh, harvest energy from sunlight. So like they are integrating with cloths, they are integrating with t-shirt and jackets. So when we talk about drawbacks. So the initial cost of purchasing a solar system is fairly high. So cost is high. Then weather dependent. Although solar energy can still be collected during cloudy and rainy days, the efficiency of the solar system drops. So during cloudy and rainy day, the efficiency of the solar system drops. So it is weather dependent. Then solar energy storage is expensive because we cannot use the same um, storage energy concept here. So here, solar system energy storage is expensive. So that is also a disadvantage. Then uses a lot of space because the solar panels. We need to have an array of solar panels. So size is very big. So uses a lot of place. So only in jacket we can have this solar panels. Uh, the same kind of device we cannot be used in like a head mount or something. Different form factors we cannot use. So we can just talk this more space. Then associated with pollution. These are the drawbacks of this solar light solutions to capture electricity from solar radiation. Next, we can go for thermal. So thermal, uh, generally thermal energy can captured from generators like thermoelectric generators. Thermoelectric generators. So by using thermoelectric generators, it is possible to convert the heat flux into electrical power. This thermoelectric generator is made of many thermoelectric elements consisting of P-type and N-type material. Each P-type and N-type material of the thermoelectric element act as a couple which generates a voltage difference. Therefore, the thermoelectric generator contains a certain number of thermoelectric elements for the generation of the power output. The generated power is proportional to the number of couples of the thermoelectric elements and to the gradient of the temperature developed across a surface. So, due to their small size and to the power output generation, these devices are suitable to the use in wearable systems. So, thermoelectric generators we are using in terms of P-type and N-type. So, as act as a couple which generates a voltage difference. So these devices are in small size, so it is suitable for wearable system. For example, here a thermoelectric watch. So here you can see the thermoelectric watch, perpetual energy source, and here it is. So the wristband. It is in form of wristband, fabricated thermoelectric generator, adhesive polymer. So these are the examples. So thermoelectric generators are less efficient than some of the other energy conservation technologies. But when we talk about the efficiency, it is less. That is the drawback of this thermoelectric generator. And the another drawback is the initial cost is very high. That is also a disadvantage. And however, lifetime cost per watt can be lower. See, the overall lifetime cost may be good, but the initial cost is very high. So due to this reason, we can go for some other concept also. So there is a fair amount of thermoelectric generator module manufacturing knowledge. However, disadvantage is the design of engineering expertise required effectively apply thermoelectric generators to an application is rare. See, during design process, applying the concept is also rare. So that is also considered as one of the disadvantage. So due to these disadvantages, we can go for some other technology and energy sources. So in this category, the next one is mechanical or vibrational. Due to mechanical or vibrational sources and the solutions harvesting energy from the body movements. Solutions based on piezoelectric. Uh, by using a piezoelectric transducer, it is possible to convert the mechanical deformation into electrical power. So, this is the concept of piezoelectric transducer. The piezoelectric transducer, it is possible to convert the mechanical deformation into electrical power. So, the piezoelectric transducer generates an electric voltage when an external force is applied to a surface in the form of pressure or vibration. So the piezoelectric transducer used for this purpose are generally grouped into two categories: piezoelectric lead zirconate, titan, titanate elements, and polyvinyl diene fluoride films. So these are the two categories of piezoelectric transducer. The former is the better in terms of transconduction coefficients. So transconduction is nothing but mm, um, it is uh, it is converting one form of signal into other form transconduction. While the second one transducers are more flexible, have uh, pyroelectric properties, and are cheaper. So, both are having its own advantages and disadvantages. So in the contemporary market, the relevant flexible and semi-flexible piezoelectric transducers are as follows: Dura-Act patch transducers, macrofiber composite, piezoelectric fiber composite, and the PVDA series. So these are the uh, available market piezoelectric transducers. So using this piezoelectric transducers, we can easily harvest energy. Using this solution based on piezoelectric effect. See here, view of the garment with the energy harvesting system using the piezoelectric effect. So in soldier, in elbow, in hip. In- So these are the places where the movement and mechanical vibration takes place, so that the movement is converted into mm, electrical energy. So here again it is elbow, elbow, is, shirt. A view of the garment with the piezoelectric element at the elbow line. So here you can see the piezoelectric element. Then what are the disadvantages of this piezoelectric energy harvesting? They cannot be used for truly static measurements, pollution free, can pick up stray voltages in connected wires. See, when we talk about static measurements and the pollution free, we cannot use because so these sources can pick up stray voltages in the connectors. So that is one disadvantage. Then low maintenance crystal is prone to crack if overstressed. So because see here how it is fitted. So if it is overstressed, there is a chance of getting crack in the crystal. So that time that the piezoelectric material will lost its characterization. Next, easy replacement of equipment. Uh, Easily it can be removed. So make it affected for a long term use. Yes, if it is used for a long term, definitely it will get affected. So because of its placement and the working condition, because whenever there is a movement, there is a vibration, it will work. So continuously, if it is used, no, there is a chance of getting crack. There is a chance of getting easily replacement of equipment is possible. So these are the drawbacks of this piezoelectric effect and sources. Then the next one is hybrid kind of energy harvesting. So in hybrid kind, how to develop textiles for human body energy harvesting. See, the concept of the development of the wearable system that guarantee the monitoring of the health and safety of human beings is to design smart cloths. These cloths could harvest the energy produced by human body to power sensors for the health monitoring. See, up to now, we studied how it may be a piezo harvester, or it is PV cell, or it may be a tag, how it is integrated with the cloth. So conductive fibers, cotton fibers. So we have the fibers in the form of conductive and cotton fibers, so in which these devices are integrated. But in hybrid fibers, there is no separate devices, piezo harvester. There is no separate sources. But no, this conductive fibers, cotton fibers are in the form of piezo fibers, PV fibers, tag fibers. So these fibers in the form of piezo fibers, PV fibers, tag fibers. So this fiber itself will act as a source of energy. So uh, clothes are not integrated with the source, so the fiber itself will act as a source of energy. So from this energy is harvested, so this is called as hybrid fibers. So in the next future, the scientific interest will focus on the development of wearable fabrics made of energy harvesters fiber. So wearable fabrics made of energy harvesters fibers. So on the one side, we are making, we are making wearable fabrics made of energy harvesting fibers. But at the other end, when we talk about electromagnetic interference and health issues, uh, we need to mitigate electromagnetic interference with the human body. So that is not discussed here. But whenever we are doing research or whenever we are implementing this, if we concentrate on that also, it will be good. Then next, mechanical vibrational solutions harvesting energy from the body movements, solution based on electromagnetic. So here, mechanical vibration, but the solution based on electromagnetic energy. So here, first we have to identify the location of the individual parts of the electromagnetic generator. The possible areas like when we are doing that is ECG. When we are taking ECG, we know how where the points where electrodes are placed. So similarly, we need to find out the location, possible areas of application, primary test locations, and select locations of retesting. And these are the areas generally in hand, in body, in legs. And generally, these are the points are used for the location of individual parts of the electromagnetic generator. Then a technical drawing of the jacket with an indication of placement of the individual elements of the electromagnetic generator. So when we talk about jacket, the place A, so this is the place A. Here we can have this electromagnetic generator, or here B place. So here it is really nearby chest, or in hand, B plus hand, we can have this electromagnetic generator. So like a typical drawing of the jacket with the indication of placement of the individual elements of the electromagnetic generator. A is the location of the coil and the accumulator. B is the location of the permanent magnet. So like we need to do all these things for mechanical vibrational energy harvesting. Then solutions based on triboelectric nano generators. See, these triboelectric nano generators are small scale energy generators that can convert the energy from movements in our surroundings into electricity. So movements in our surroundings is an example like a human motion, machine vibration, vehicle movements, wind, and wave energy. So this tribo nano generators, the name itself is a nano generators, are the small scale energy generators. Small scale energy generators. It will convert the energy from movements in our surrounding into electricity. So what are the movements in our surroundings? For example, human motion. So when the place where humans are moving here and there, so machine vibrations, when the machine is running, that vibrations takes place. Then vehicle movements. So vehicle movements in the road, we can get wind. So due to wind and wave energy. So from all these things, this is in our surroundings, movements in our surroundings can be converted into electricity by using this tribo nano generators. It is a small scale energy generator. These generators work based on the combination of two common effects, triboelectric charging and electrostatic induction. See, triboelectric charging or static charging is typically an undesired effect we experience in everyday life. Generally, when we talk about electrostatic induction, static charging is an undesired effect. With respect to EMI, EMC, is an undesired effect. But but
Okay. So,
but it is very useful here. But it is very useful here. So the same static charging is positively used in this concept, the triboelectric nano generators. These are made of dielectric materials such as plastic, which can accumulate triboelectric charges when they contract or rub against each other. When this occurs, one of the surfaces will be positively charged and the other will be negatively charged. See here, it consists of metal layer 1, metal layer 2, plastic 1, plastic 2. So when these two triboelectric charge are created, positive and negative, so it can act as a small scale energy generators. So here it is an example of electromagnetic energy generators. So here human body motion is highly regarded as a promising source of energy for powering body moving electronic devices and health monitoring sensor. Human body motion we can use. So transforming human biomechanical energy into electrical energy provides sustainable energy to drive those devices and sensors, reducing their battery dependency. Because sensors needs low power, even though it is a low scale energy device, it is used to, it is enough to power the sensors. This work presents a fully enclosed wrist wearable electromagnetic triboelectric generator, or it incorporates rolling electrostatic induction and electromagnetic induction using freely moving magnetic coil inside the hollow circular tube. See, the materials used in 3D printing technology are used as energy harvesting materials for easy and quick worthwhile fabrication of the uh, this electromagnetic triboelectric energy generator. A thin, flexible flux concentrating material is introduced to increase the EMF and enhances the electromagnetic performance. Um, so this nano generator harvests energy under the diverse circumstances and irregular wrist motions such as swinging, waving, shaking. Following the experiments says, so this generators, this small scale generators can give average power density of 0.118 microwatt and can drive a commercial wristwatch continuously for more than 23 minutes from just 5 seconds of wrist motion. So if you are making 5 seconds of wrist motion, it generates 0.118 milliwatt power. So it is useful to run the wristwatch for more than 23 minutes. So, so, so most of the wearable devices are using this concept. This concept. Then solutions based on dielectric elastomers. Dielectric elastomers are mechanical sensors that can be used to measure deformations, forces, and pressures and consist of elastic elastomer coated on the both sides of the highly flexible electrodes. It's nothing but mechanical sensors. The sensor affects systems from the measurement of the electrical capacitance. Under the tensile loading deformation, the surface expands and the thickness of the sensor film decreases, causing an increase in the capacity value. So, so under the tensile loading of the deformation, the surface expands and thickness of the sensor film decreases, causing an increase of the capacity value. The elastomer film is generally made of silicon rubber, natural rubber, acrylate, or polyurethane. The hardness of the elastomer determines the sensitivity of the transducer, or we can say while being more commonly used as sensors, they have also been studied as possible power generators. So finally, we can say the solutions based on dielectric elastomer. This dielectric elastomer is a mechanical sensor. It can be used as a so this picture shows how there is a undeformed and deformed kind of single actuator in contact with state, how it is happening. So these are the different types of energy solutions, energy sources we discussed. Then, see, all these energy sources, energy solutions are having its own advantages and disadvantages, and uh, under mm, the major thing is cost, and also the size and shape. So materials, how much amount of power we can generate. So these are the factors. This is finally RF energy harvesting. So this RF energy harvesting, already we said it is from ambient energy. So radio frequency energy harvesting is the form of the wireless power transfer technique. For example, you can say transmission antenna, RF generator. The transmission antenna is transmitting the RF signal. So it can be because nowadays we can see lot of RF energy is available in the environment, like ambient energy. So this energy can be easily tapped by using receiving antenna. So according to the available EM energy uh, with the frequency, operating frequency, the same antenna is designed as a receiving antenna. So after this receiving antenna receives electromagnetic signal from the ambient energy environment, it is given to the impedance matching network, and then rectifier voltage, then power management, then applications can be used for wearable devices applications. So this is the general idea about RF energy harvesting. Here, mm, so this receiving antenna and mm, received power, receiving antenna and converting into the DC power. So the output of the receiving antenna is AC. So using some circuit concept, we can convert into that is using impedance matching and rectifier voltage, we can convert into DC power, so that can be used for the devices. So that after this RF generator transmitting antenna, the receiving antenna, impedance matching, rectifier voltage multiplier, filter network, power management applications. All this will come under wireless power harvesting circuit. These are called harvesting circuit. Also, it is called a rectana. Rectana. So, uh, so rectana design. When you are designing harvesting circuit, rectana design is very important. So rectana includes receiving antenna plus rectifier. It's called rectana. So introduction to rectana. Rectana is nothing but a rectifying antenna. So rectana elements in the proposed system consist of uh, compact receiving patch antenna. It may be any kind of antenna, but here it is given as patch antenna because I think other than patch, all kinds of antennas are in very big size, but we can have in the form of monopole type of can use. So here, for example, this is patch antenna. Then the LC transform microstrip matching circuit is needed. Then dual diode rectifier circuit, mostly used to diode is Schottky diode. Then LC transformed microstrip band pass filter circuit. Then storage capacitor, resistive mode, it is in between 10 to 75 for powering sensors. Then performing goals. See, receiving antenna, when we are designing receiving antenna, it should be a high gain antenna, high directivity, high efficiency. VSWR is greater than 2 and 50 input impedance. Then rectifier, high DC voltage and high efficiency. Rectifier should be designed for high DC voltage and high efficiency. Then applications of rectana is uh, generally when we're talking about rectana, it is for wireless power transmitter, or we can use for energy harvesting circuit for wireless sensors. Uses in the water. So hyporectana, we can do wireless power transmission. So these are the general idea about rectana. How what are the components need to design rectana, and rectana is nothing but it consists of antenna with rectifying circuit. Uh, rectana is also called as energy harvesting circuit. So when we talk about RF energy harvester, it consists of receiving patch antenna, matching circuit, dual diode rectifier circuit, uh, band pass filter, capacitive storage, resistive. So like we can easily design uh, mm, energy harvester circuit. See, in this energy harvester circuit, uh, the design challenge is included with both the antenna and the matching circuit. The next requirement and challenges in designing rectangle. So when we talk about the requirements in designing rectangle, we can say it is a simple rectangle topology. So when we are designing this rectangle, the topology we have to choose a simple topology because when we talk about antenna, the antenna may be a single antenna or an array kind of antenna. Uh, the antenna may be a narrow band antenna or a wide band antenna. So according to the type of antenna, mm, the matching circuit will vary. The topology will vary, the overall topology will vary. So whatever it may be, better we have to choose a simple rectangle topology. Then compactness. So compactness is very important when we talk about wearable devices because wearable devices, the main um, advantage of wearable devices is hands-free nature. So if it is a hands-free nature, when it is mounted on a part of the body, when we are wearing that devices, the size of the antenna is very big. Harvester circuit, the overall circuit is very big, means it is very difficult to carry. So compactness is very important. So rectangle components and materials. Uh, so when we are choosing a rectangle components, instead of lumped components, we can go for
நான் போட்டிருந்தா கொடுத்துருப்பேன் ஆனா நானே
instead of the lumped components, if we go for a distributed components, PCB kind of component, so it occupies less space as well as the weight will be reduced and the materials. So similarly, depends on the frequency, material will vary. Depends on the operating frequency, material will vary, and depends on the dielectric constant, material will vary. Depends on the size also, material, because if you go for a high dielectric constant, the size is the antenna size will be small. So we have to choose the material according to the required shape and the size and the operating frequency. So these are plays an important role when we talk about rectangle design. Then next, the challenges in designing rectangle, comparative trade-off between receiving antenna size and the gain. See here, gain and this size are having trade-offs. So how we are choosing, because if we need high gain, we need to go for a more area on the specific size. So how we are going to, but here no, according to our thing, we need to design a small size, but we go for a gain, the area of the um, I mean, radiating area will be increased. No? So when we increase radiating area, then only we can achieve high gain. But we need to design a small size antenna. So there is a trade-off between size and gain. So that we have to decide, that we have to make optimum. Then next, trade-off between losses and the power by properly matching receiving antenna to the rectifier. So here, how we are going to make a trade-off between losses and power by properly matching device and rectifier. See, because the matching is not perfect, whatever the power we are receiving, it will not transfer to the storage device. So we have to design a proper matching circuit so that if the matching is 100% perfect, the 100% energy is transferred to the storage device. Otherwise, we need to face many losses. Even though we harvest more energy, it will not be transferred to the storage device properly. So matching a circuit is very important when we are doing the design of that kind. Then achieving bandwidth utilizing single antenna element. See, when we go for sometimes we need to design broadband antenna. It is wide bandwidth antenna. So when we are designing wide band antenna, we can go for an array. But here in this case, if we go for an array, it will increase the size. So without array, within a single element, single antenna element, how can we increase the bandwidth? So that is also a design challenge. Then designing receiving antenna based on the operating frequency of the transmitting antenna. See, according to the ambient energy available in the area, the where the device is operated. So according to the available ambient energy, according to the available ambient energy frequency, ambient, that is EM wave frequency, we need to design receiving antenna. So that point is also we need to consider when we start our design. So these are the requirements and challenges in designing antenna. Then generally antenna design and measurement, when we talk about that is harvesting, energy harvesting antenna, or it can be called as the receiving antenna, because energy harvesting antenna is nothing but receiving antenna. It is not a transmitting antenna. So it is called as a receiving antenna. So receiving antenna types based on the bandwidth. So bandwidth, it may be, see, in energy harvesting type or receiving type, we need to have a narrow band receiving antenna for some applications. Sometimes we need to have wide band receiving antenna also. So when the frequency is very high, when the operating frequency is very high, obviously the bandwidth is wide. So in case of single band receiving antennas, we can have these types. That is, if you want to design single band receiving antenna, you can have patch type, dipole type, monopole type, ferrite rod, slot, loop, pixel. So these are the types. If you want to design multi-band, so because if suppose your ambient energy with three different frequency, so that time we need to design multi-band antenna. So for a multi-band antenna, we can have these types: monopole, slot, Vivaldi. So these are the antenna types used to design multi-band antenna. So these are from literature. And for designing wideband receiving antenna, we can have patch type and monopole, ferrite rod, slot, loop pixel, Vivaldi, spiral, log periodic. But for multi-band antenna, patch, dipole, slot, log periodic. So from this, it is very clear, except multi-band, um, for all the category, we are having patch antenna, because the reason is uh, the size of the antenna is very small. We can make it small by selecting proper material and the dielectric constant. So patch antenna is there. So here is the example of one receiving antenna for RF energy harvesting of wearable sensors. It is nothing but a square patch antenna with a center feed. Here it is the 3D view of this receiving antenna. The substrate definition is given. So this design theory software. So it's free space, conductor one, pole, and conductor. So here the used material is washed cotton, 3 mm thickness, yes, with two conductor. So here PC wire is added in this design. So there is a PC wire from bottom layer to top layer. So like this center feed antenna. So this center feed antenna is operating with a frequency of 2.4 gigahertz. That is ISM frequency. So this antenna can act as a receiving antenna. So we can, whatever the EM is available at the 2.4 energy, that is ISM line, it can harvest it. It can act as a receiving antenna. It can harvest the EM energy. With the help of rectifier circuit, we can convert into these waves. So here, this is one example. This is another example. Characteristic RF energy harvester for smart agriculture sensor. So here, so this antenna is also operated at the frequency of 2.4. But if you are seeing this PCB board, this array antenna, this 4 arrays, 1, 2, 3, four arrays are built in a series manner, series filter antenna. It is a kind of PCB antenna, but here some of the wire holes are placed so that the antenna characterization is improved by using wire holes. It is in the form of SAW antenna, the substrate integrity, using wires to convert the PCB into substrate integrity. And this antenna is operated at the frequency of 2.4. By using this this four array antenna is when it is connected with the rectifier circuit, and the load is giving the output voltage of 93 microvolt for 22 load. So that according to this formula, we are getting the efficiency of 45.45. So for other resistors, and the voltage is different, and efficiency percentage is also different. But for this 22 ohm, we achieved a high efficiency, 45.45%. So this voltage and power can be used to power up the sensor network. So that is why it is used for smart agriculture sensor. Actually, this antenna design and after fabricated with the rectifier circuit, we tested, and these are the results we got used to do also. So this is just for example I have this. And so when we talk about this, wireless, yes, wireless power transmission. So wireless power transmission, and also the wideband antenna. Or when we talk about this wideband kind of antenna, wideband receiving antenna, mostly when we talk about wearable devices, the receiving antenna we need is narrowband kind of antenna. This wideband antenna, is we also done one wideband antenna category for the satellite health monitoring. So the wideband antenna is designed for a KU band. It is designed with wideband matching circuit. So both the wideband antenna matching circuit, we used it for satellite health monitoring. So because satellite health monitoring system consists of lot of sensors. So to power up those sensors, it's wideband antenna and the wideband matching circuit at KU band design. We published as a paper. We published in IET journal as well as circuit work. We published two journals in wideband category. This is under the narrowband category. Next, the topic is self-powered wearable electronics. See, when we talk about wearable electronics, see, most of the system or concept or technology says it's not self-powered. So we need to do manually, or we need to replace, or we need to have some sources. Uh, so or battery operated. So in these cases, the lifetime is very less. It cannot work out for a long time. It's self-powered. Once we design, and it can be operated for a long time. So self-powered wearable electronics. Self-powered wearable electronic systems are designed by collecting energy or information from the environment surrounding the human body. For collecting energy and collecting energy and for collecting information are two different applications. Let us discuss with them. See, that collects energy around the environment and applies it to the other wearable devices. We call it as energy type, self-powered wearable technologies. or collect information around the human is the sensor type. So there are two types. One is collect energy around the environment. Collect energy around the environment is energy type. Another one is collect information around the human is sensor type. So these there are two different types of self-powered wearable electronics. Both of them have wide range of essential applications in the field of biomedicine, military, wireless communication, and wireless sensing. So next we are going to see about self-powered wearable electronics. See, under this self-powered wearable electronics, the first example is self-powered sweat monitor. This self-powered sweat monitor, uh, there are different types. So see the picture A. A, it is a multiplexed into situ respiration analysis system based on the flexible integrated sensing array. So we have sensing array, respiration analysis. See how the sweat is sweat from the sweating, uh, that is watery kind of things will be analyzed, analyzed by using flexible integrated sensing array. So here array of sensors are available. This is to test the perspiration analysis. So it is a self-powered one, and the B, the picture B denotes it is non-invasive electronic skin based on piezo biosensing unit matrix. So here mm, sensors used, but in the second example, piezo biosensing unit of matrices used to used as a self-powered sweat monitoring. Self-powered electronic skin based on the triboelectric biosensing unit matrix. Yes, triboelectric biosensing matrix. And uric acid monitoring system based on the entirely uh, laser engraved wearable sensors. So, so if we talk about this self-powered sweat monitor system, the sweat monitor system in different sources, using different sources. So here sensing array, here piezo biosensing unit matrix. Here it is a triboelectric biosensing unit matrix. Here it is mm, laser engraved wearable sensors. So various sensors, various sources, various matrix forms are available for the self-powered sweat monitor system. So this is one type is used for sweat monitor. Similarly, self-powered body temperature monitor system and self-powered respiratory monitor system. So in this mm, temperature monitor and respiratory monitor, self-powered temperature sensor based on the pyroelectric nanogenerators. Already we discussed pyroelectric nanogenerator. Using this concept here, it is the self-powered temperature sensor. And self-powered temperature pressure dual parameter sensor fabricated by organic thermoelectric materials. Then picture C shows that the wireless temperature sensor system based on the hybrid nano generator. And picture D denotes, if you are seeing this D, wearable self-powered active sensor for respiration monitoring based on the flexible piezoelectric nano generator. So this one is the D is flexible piezoelectric nano generator. So this type of source also we discussed. So this temperature monitor system and respiratory monitor system used various types of sources and generators. So wearable respiration sensors based on pyroelectric nano generator integrated with an N95 respirator. See, we are using N95 mask. So here, what is mean by N? N denotes what? 95 denotes what? See, N denotes the different ratings in place for respirator indicate how well the mask will protect against oils and are rated as N. Or it is R. Otherwise, it is P. So according to NIOSH, NIOSH is nothing but National Institute of Occupational Safety and Health. So according to NIOSH, respirators are rated N if they are not resistive to oil. If it is R, it somewhat resist to oil. If it is P, strongly resist oil proof. But our N95 mask is not resistant to oil, not resistant to oil. So that is why it is denoted as N. So 95 denotes the number of respirators that filter out 95% of airborne particles are given as 95. So it filter out 95% of airborne particles. So that is why it is denoted as 95. So N is nothing but N is nothing but the mask is not resistant to oil. 95 denotes 95% of airborne particles are filtered out. So that is why it is called as N95 mask. So we can do the design for N99 also, N100 also. There is a design challenge using different materials or different concept. Then airflow driven triboelectric nanogenerators used for monitoring both breathing status and exhalation water. So these are the different examples of a self-powered body temperature monitor system and respiratory monitor system. Just example. So next is self-powered pulse monitoring system. So in pulse monitoring system also, ultra thin epithermal piezoelectric sensors are used for real-time arterial pulse monitoring, and flexible self-powered ultra-sensitive pulse sensor based on triboelectric effect. Then self-powered ultra-flexible biosensor based on nano-grating pattern organic photovoltaics. Then moisture-driven flexible multifunctional sensing system based on the flexible piezoelectric sensors and moisture-enabled power generator. So these are the examples. So self-powered pulse monitoring systems are many types are available. See, A, B, C. So these system used different types of sensors and different technology, different concepts. The self-powered drug delivery system. So even we are using self-powered drug delivery system, trans-scleral drug delivery system. It is given by A. For I think for I. For B, self-powered electroporation intracellular drug delivery system. So it is B. It is for rat. The C, self-powered controllable drug delivery system for highly efficient in vivo cancer therapy. So vivo cancer therapy is here it is a self-powered controllable drug delivery system. Yes. Here. Then the fourth one is self-powered on-demand transdermal drug delivery system, self-powered wearable antiphoretic transdermal drug delivery system. So these are the different types of drug delivery system used in medical field. So all these systems need self-powered sources of energy. Next, self-powered tissue repair system and the self-powered nerve muscular stimulation system. So, when we talk about electrical bandage for accelerating skin wound healing, or sometimes self-activated wearable electric stimulation device for effective hair regeneration. Now, in health department or beauty department, or cosmetic department, this is self-activated wearable electric stimulation. In self-powered TNNG-based system for direct muscle stimulation, uh, so for patient muscle stimulation sometimes the treatment. So that time also we need to seek for self-powered auto-operate neural stimulating e-skin for characterization. So for all these types factors of synaptic plasticity, for all this application, we need self-powered kind of thing. So there is a chance of using this self-powered concept for all these applications. The self-powered motion information detecting system. Motion information detecting system for man. Multifunctional change monitoring system based on triboelectric generator. Then underwater wireless multi-site motion monitoring system based on ionic structural nano generators. Self-powered GPS location system based on battery-like self-charge modules. These are information detective systems. Then man-machine interactive systems. In robotics, self-powered triboelectric or auditory sensor for social robotics and hearing aids, and rotation sensing and gesture control of the robot joint via triboelectric condensation sensors. So these are the example of a self-powered man-machine interactive system. So you see the next okay picture. So from this we can understand when we talk about the self-powered wearable electronics, how the self-powered systems are spread around for various applications, for various sources, for various generators, for various types. In various types, it is available. It is used in various fields like healthcare, medicine, beautician, and cosmetics, and medical field, in general, wearable respiration sensors based on this N95, like N95 respirators. So various in medical field also in various applications, as a drug delivery. So in all these applications, we need self-powered systems. So you see the demand of wearable technology as well as the design of energy harvesters. Energy harvesters maybe from different sources. Nowadays, the researchers are concentrating more on RF energy harvesters. When we talk about the future development trends of wearable electronics, so integrated self-reliable electronic skill system, that is an important area. Then wireless body area sensor network system plays a major role. Then wireless skin interface to biosensors for newborn physiological monitoring. So, so how wireless skin interface to biosensors making, so that is plays a major role. And skin integrated wireless haptic interfaces. So these are the future development trends in wearable electronics. So on the body, near the body, so already we have many applications. We are using those kind of devices, but in future, it is important to concentrate on integrated self-healable electronic skin system, wireless body area sensor networks, or wireless skin integrated biosensors for newborns monitoring, psychological monitoring, or skin integrated wireless haptic interfaces. So these are the future development trends for wearable electronics. Then materials used in self-powered wearable electronics are thermoelectric pyroelectric generator. In this kind, we are using anti-wind bismuth. If it is a piezoelectric generator, PVDF and ZM, so this material. With a solar battery, no, CIS and CDT, these are the materials. If it is triboelectric, means it is PTFE and PTFS. So PTFE is nothing but polytetrafluoroethylene. PTMS is nothing but polydimethyl siloxane. So PVDF is nothing but polyvinyl chloride and acetone is oxide. So these are the materials we are using for different types of and four kinds of primary ergonomics methods of self-powered systems, wearable electronics. See what is meant by ergonomics? So ergonomics. So ergonomics are nothing but human factors is the scientific discipline connected with the understanding of interactions among human and other elements of a system. The profession that applies theory, principles, data, and methods to design in order to optimize human well-being and overall system performance. So, and again, ergonomics denotes the human factors. Four kinds of primary ergonomics method. One is fabric-based wearable devices. Another one is utilized flexible stretchable substrate to construct an electronics body interface. Then bound devices with the axillary tools. Then integrate devices with wearables. So by these four wearing strategies, this self-powered wearable electronics can contact with the human body closely and firmly and collect energy or signals generated by the human body effectively. So these are the four methods you can follow for designing this self-powered wearable electronic devices. So the next conclusion of this presentation is, see, uh, we discussed what are wearables, what are the design considerations, and different types of sources, energy sources, then energy technologies, and uh, link between sources and technologies, how we are implementing, what are the methods we are using, where we are using, what are the different applications are available for this for wearable electronic devices, and the different types of energy harvesting systems, and finally self-powered wearable electronics. So because nowadays the recent trends focusing on self-powered wearable electronics. So when we are talking about self-powered wearable electronics, the sources may be from any type. Sources may be sources and generator from any type. So depends upon the situation, depends upon the application, depends upon the uh, place where we are using. It will vary. So self-powered wearable electronics has received extensive attention and research due to its probability, wide application space, and the high value of future market. So in the future, the combination of materials with the new features and the new functions, wireless, passive, soft, and easy to wear, good safety and stability, facing practical, clinical, and market applications will be the development direction of the next generation of wearable electronics. Meanwhile, the hybridization of these new technologies and self-powered system will further promote the development of the self-powered wearable electronic devices. So the recent research mainly focusing on self-powered wearable electronic devices. So we have discussed some of the applications. Apart from this, so many applications are available. Um, when we talk about the self-powered electronic devices, energy harvesting circuit plays a major role. Um, Nowadays, RF energy harvesting is plays an important role. So I think RF engineers also can contribute their technical expert in this self-powered wearable electronics devices as by designing retina or receiving antenna with rectifier circuit. That's my conclusion. Thank you. If any queries, please.
Thank you, ma'am. Thank you for presentation. Now I request our participants to place the queries to the speakers.
Good afternoon, ma'am. This is Mohammed Hashim,
Yes.
head of the informatics station.
Yes.
My question is, you was talking about self-powered wearable devices,
Yes.
and how these self-powered wearable devices will have the effect on ambient assisted living, like elderly health monitoring and differently abled people.
Self-power. See, wearable devices or wearable technology is nothing but it consists of smart devices, smart IoT devices or sensors. So these sensors will collect the information about the human health conditions. It may be heart rate, it may be pressure, or it may be heartbeat, or it may be how much calories burned. So like all information will be collected by using sensors. So the wearable device consists of lot of sensors, many number of sensors used for various applications. So these sensors can be powered by harvesting circuits. So the harvesting, if it is self-powered in the sense when this harvesting circuits collect energy from ambient, this ambient energy will be collected. That's by using RF harvesting. RF harvesting. See, RF harvesting is the um, RF harvesting is the um, only subject it can collect energy from ambient. So if we use RF energy harvesting, we can easily self-power the sensors. So it means we should not use other concepts. So it is not like that. We can use other concepts also. But if nowadays, in recent trends nowadays, we are concentrating more on RF energy harvesting. So because you see, for example, wherever we go, EM energy is available. So we are having many applications like mobile phones, Wi-Fi. Yes,
Yes, ma'am.
there are so many EM waves, ambient energy as EM waves are available in the environment. So we can harvest those energy. We can convert into a DC power. It can be used for powering sensors. Sensors are IoT devices, smart devices that is used to collect information of our body, and automatically it will transfer into laptops or mobile phones.
Okay, thank you. One more doubt, ma'am. What about the precision and accuracy and even the selectivity part of these smart devices, ma'am?
Accuracy and activity, it is based. That is why in design consideration, I have given like form factors where we are going to place this wearable device. According to that, we have to choose the size and shape of the wearable device. And the other application is like how many sensor we are going to use. So if it is 5 sensor means all 5 sensors need how much power. So is it enough to give 5 volt power from RF energy harvesting from this area, or it is not possible means we have to go for another type of energy sources like piezoelectric sources. So like according to the situation, according to the application, we need to choose the, we need to design the wearable device as well as mm, the harvesting circuits, everything.
Thank you, madam. Thank you.
Good afternoon, madam.
Yes, sir.
Am I audible?
Good afternoon. Yes, good
Yes,
afternoon.
yes,
Good
sir.
afternoon. Ma'am, just wanted to know, in the design of the devices, you told the main important factor is the form factor.
Form
Whether
factor
that
is,
form factor is a quantitative parameter or qualitative parameter, and whether a form factor is decided earlier the design or after the product is designed, the form factor is known.
yes, sir. Discussed about form factor. Uh, See, form factor is nothing but it defines the usefulness of the device, or we can say it defines the size and shape and how users wear or carry it. See, suppose if we design one wearable device, uh, we have to decide where we are going to fit this wearable device in our body. That we have to decide.
Okay.
Is it correct? So that is decided by these form factors. So because if we choose the form factor is uh, watch, it is a kind of a watch. So we must wear in hand. We cannot wear in head.
Okay.
So according to that, we have to
Okay.
fix the size and shape.
Oh, that you mean to say all watches have the same form factor?
Yes.
All
So,
smart watches have the
watches.
same form factors or they differ? All watches have the same form factor?
Not same form factor, but if it is watch now, we need to have this much size, this much shape. It should not be, see, maximum possible. Maximum
Then the
possible.
form factor is computed.
Yes, we can compute. We can compute form factor. There is a method. There is a method.
Okay.
We can compute.
Okay.
So according to
Thank
the
you.
physical size,
Okay. Okay. That means it is a quantitative parameter.
quantitative parameter.
Okay. Thank you. Thank you.
Good afternoon, ma'am.
Good afternoon, sir.
Is it audible, ma'am?
Yes, audible, sir.
Very good presentation, ma'am. We learned many things. So my question is,
Yes, sir.
what are additional requirements and features required harvesting antenna when compared to ordinary antenna?
Compared to ordinary antenna, what are the additional requirement of harvesting antenna?
Harvesting antenna.
First thing, always you should have in your mind, harvesting antenna is a receiving antenna. It's not a transmitting antenna. And when we are designing a receiving antenna, first we should concentrate on operating frequency. How we will decide the operating frequency? We have to design the receiving antenna according to the transmitting antenna operating frequency. See, if you, because we are harvesting energy from ambient in the sense, first we have to identify what are all the frequencies are available in the ambient. So when we are designing our receiving antenna, it may be a single band antenna because only one frequency is available in the ambient. So that time it is a single band antenna. So three frequencies are available in the ambient. So we can design our receiving antenna as a multi-band antenna. Or very high frequency is available in the very high frequency, very wide range of frequencies available in the ambient, so that you can go for wide band. So like according to the environment and the ambient energy availability, we have to choose the type of antenna. And after choosing the type, if it is, as I mentioned in here, if it is narrow band means we can go for this type. Multi-band means this type. Single band means this type. In wide band layer, single band, multi band. These are the types. This is generally literature. From the literature we have taken. These are the types already the researchers they have published for as a receiving antenna. They also proved their performance. You can go for these types. Uh, then according to that, matching circuit will vary because narrowband matching is very easy, but when we go for wideband matching, it is very difficult. So matching design is also very. So after designing matching circuit, uh, it is very difficult to use matching circuit in the form of distributed component, that is RLC component. Uh, it will not work out. So we have to go for the PCB kind of distributed component matching circuit, distributed kind of matching circuit, PCB kind of matching circuit. Then again, then at last, the energy storage capacitor and load.
Excuse me, madam.
Yes, yes, yes,
Can you hear me, please?
yes, 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 yes.
My question is
Audio.
like, because we have a antenna in our mobile phone,
Mm.
can we use the same antenna for energy harvesting, or we have to have another antenna? Like-
Your
My question is
Yes,
like,
yes.
while
Yes,
I am
yes.
talking, as there is everywhere radio energy is available,
yes, yes.
if we could harvest it better, we don't need to recharge it. Like, is there such possibility?
So you want to use your mobile phone antenna as a receiving antenna.
Yeah, can we?
So uh, your antenna already it is acting as a receiving antenna as well as transmitting
Yeah,
antenna.
we have a duplexer over there. It
Duplexer.
works for both.
Duplexer. Yes, if you are attaching your antenna, your mobile antenna with the rectifier circuit and energy storage device, yes, definitely you can harvest some energy because already it is operating with EM waves. It is transmitting, but whenever it is receiving, it will convert energy into DC.
No, there is a problem, while we are receiving, we will be
Yeah.
receiving particular frequency channel. Let's say it is GSM.
Mm.
One particular frequency channel is assigned for call conversation,
Mm.
and we will be receiving from the base station.
Mm.
While
So
we are, while we are,
whenever your antenna is receiving, that time that energy is converted into DC.
parallelly,
Parallel. Yes, 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 we can do. Yes, we can.
what is the traditional circuit we need to have over there? Is it, as you said, is rectifier, and then what?
Rectifier. See here, see it's a kind of PCB.
Okay, if it is beyond, please let us not. Please.
Rectifier, that,
Okay.
storage capacitor and load. So see, for testing purpose, we attach this load. Just, you can drop a DC across this load.
Mean to say we should have a separate track for that, right?
Yes, yes, yes. Yes, yes, only you need to connect matching circuit, rectifier circuit with your antenna.
And madam, if we connect a rectifier circuit to the antenna while we are receiving, there is another impedance matching problem will be there. It's not so easy, with a RF range.
So that is why we are matching circuit. No, in between.
Because we are
can
dealing
have-
with very tiny signals, in the micro volts like
Okay.
signals, minus 100 dBm, something like signals we will be receiving from the base station.
Mm.
And if we add something to that antenna while we are receiving, as we said, it's a rectifier or some other circuitry.
Okay.
If there is a impedance mismatch, we'll be losing what the transmitter is saying. A meticulous, separate track must
Sir,
be there.
yes, yes, but here we are see we are not taking the information. We are taking only the frequency, no? Frequency. It is energy, EM
Yeah,
energy.
madam.
EM energy. It is not information. So we are not touching with information. We are taking only energy. I think it will not have any. With the matching circuit, if we design the rectifier circuit, it will not have any problem.
Thank you. Thank you.
Yes. You test it and tell me, sir. It is my from the experience,
Yeah, madam. Please, please.
research I'm telling.
Yeah, that's what.
So this example, I have done the research with this example. We got some, yeah, my paper, sir, energy harvester for satellite health monitoring by Dr. Umma Habiba and my student, Miss Revadi. Recently, we published our paper, energy harvester circuit paper in Circuit World, sir. If you search now, you will get Circuit
Sure,
World.
sure, madam. I'll go through. I'll go through.
Circuit World and IET communication.
Yeah, yeah. Thank you. Thank you.
Yes, sir.
Good afternoon, madam. Can you able to listen me?
Yes, sir. Yes, sir.
Madam, how much maximum power can be harvested using this RF harvesting techniques, RF antennas?
According to the literature, maximum of 5 volt they are saying, sir.
In terms of voltage, you're saying in terms of watts?
In terms of watts, they are saying from the light it is 15 milliwatt, from vibration it is 20 milliwatt, from thermal it is 10 milliwatt power. So in RF wide range, so according to your design, according to your antenna design, according to your matching circuit design, it will vary. So wide range here also it is possible. So in terms of voltage, they are saying here it is 10 volt, 10 tens of volt, here 5 volt. So like.
Thank you, ma'am.
Yes, yes, yes.
Hello,
Okay.
good afternoon, ma'am.
Yes, yes. Good afternoon.
Ma'am, I have one question.
Yes.
In self-wearable devices, you have mentioned that TENG and PENG materials were widely used. Is there any other materials currently available apart from these two, ma'am?
Actually, when we come to material selection, it plays an important role. See, nowadays, material characterization, finding new material is again the another topic of research. When we talk about nanotechnology, when we talk about what is that? Selecting material for different applications. So it plays an important role. So material selection. So even you can characterize new material with a different dielectric constant. It is more suitable for giving this getting harvesting more energy. You can characterize your own material also. So when we talk about material, see there are journal is called study of material characterization. Like many journals are available. So if you go through those journals, you can easily find out any new materials are proposed for this kind of application. Or if you search in the Google, or generally when you are choosing material according to your application. See when suppose if you are designing one antenna or you are designing one wearable device sensor. So what are the requirements? Where it is operated, up to which temperature it should be compatible. So like by getting all this information, if you search in the Google, which material is suitable for this application. So for example, Rogers. Rogers is the is a US material manufacturing company. So if you search in Rogers website, you can find out which material is suitable for your application. It may be an antenna or it may be a sensor. So you can purchase those material in that company. Or if you find out generally in Google, these are my criteria. I want a material to satisfy this criteria. Even Google will tell you, nowadays Google is more brilliant than us. Google will tell you many solutions, many things. See, always as a researcher, I'm telling because I'm having 15 years of research experience. As a researcher, I am telling, no need to nowadays, no need to worry about anything. Whatever you want, you search in the Google. Whatever you want, just the question you type in the Google, you will get a lot of information. From that, you can easily choose.
Okay.
So,
Thank you. Thank you.
Okay, ma'am. Thank you for excellent presentation. And we are going 15 minutes ahead of the presentation. Our next session starts by 3:30. Once again, on behalf of the management as well as the coordinators, I thank Dr. Umma Habiba Madam for her excellent presentation in our 5th session of this 5-day FDP program. Once again, thank you, ma'am.
thank you.
Thank you, ma'am.
Thank you so much. Thank you, participants.
So the feedback link will be shared in the Zoom meet. Participants can take your own time and you can join by 3:30 in our next session by Dr. Muhammad Rizwan bin Ahmad, joining us from Malaysia, Faculty of Engineering, University of Technology, Malaysia. Since we have fewer time, I want to quit this session 5 in the Zoom and I want to start the session 6. So you cannot proceed on with the same feedback link as posted in the Zoom. So we request the in charges to post that link in the Zoom, that is the WhatsApp group. So you can give your feedback from the WhatsApp also. This is exclusively for this session alone because we are going over the time. So it will be overlapping with our next session. I want to start up the new link with the next session. So you can give your feedback link as well as attendance from the WhatsApp also. Thank you. As the session links are not same, we have been shared the new session link for the 6th session. So I request the participant to join using the new link.